Okay, good afternoon, everybody. So, couple quick announcements today. The biggest two things, your Canvas Quiz 3 is due today at 5 p.m. Tomorrow, Canvas Quiz 4 is going to open right away. So this is going to have some pacing, so you have practice things to work on as we walk up to the midterm. Also, as a reminder, meet and greet is today in D215, $5 cover, money well spent. Last class, we talked our way through enolates, and these are additions of enolates. Now we talked about things like the intramolecular aldol reaction, and we jumped away from normal enolates where we have enolates on aldehydes or enolates on ketones, and we start moving to enolates on esters. So still carbonyl compounds, different pKa. Because that different pKa is slightly different game. Also, since you're at a higher oxidation state, you're not just adding a carbonyl into an aldehyde or a ketone. Now we're ejecting an OET or some other sort of group. That gives us our reactions, what we call the Claisen and the Dieckmann. Same thing, only difference is Claisen is two esters, two different molecules. Dieckmann is just one where those two are attached together. The donor and acceptor are part of the same molecule, but functionally the same part. Last thing we brought in is kind of what happens after. We use reactions like the Claisen to set up these systems that have these 1,3 dicarbonyl systems. These things where you've got two carbonyls and a proton in between. That's what we call our malonic ester synthesis. That's where we're now using this to acidify or target a group. So here's your review question. If you have these two components in these conditions, what is your product? Okay. So let's break down this into a couple different pieces. We have our two components. We have a base. This is a two-step process, first step, second step. The first step, second step is there for our reaction and then our workup, right? Now, since we're treating with a base, first thing we're going to look for is, are there acidic protons? And we want to sort of just break this down into the components of the molecule. We're looking, if this is something like an aldol or a Claisen reaction, you're looking for two components. One's your donor or your acceptor, or nucleophile electrophile. So we have to assign those roles. If I'm a base, I need alpha protons. So that's red molecule versus blue molecule. Which one of these has an alpha proton I could deprotonate to make my nucleophile? Red or blue? Red. Blue is out. They both have carbonyls, but only this center has alpha protons. So my base is going to make my enolate. So that's my donor. that one is an obligate acceptor. It cannot be deprotonated. It's just an electrophile. So we're going to add to that fraction. So that addition is going to look something like that. That's going to be your nucleophile goes up. You make a tetrahedral intermediate. That intermediate will look like the red fraction after it's added now. We have our new bond we just formed. And we're going to have O minus, O ethyl, and the other aromatic group. And this will collapse and kick out our OET group. Final product we should have here is going to have the donor part of the molecule, the new bond, and the acceptor. So each of these, right, as you go through and do the aldol, Claisen, any other component, first step is get the roles right, figure out who's who. In a case where we had to make a decision, more than one alpha proton, that's where maybe acid base is going to matter. Which one is more acidic or something like that. But there's a simple dimerization between these two fragments to make these kind of dicarbonyl ones. This is the hallmark of sort of the Claisen reaction. So today we're going to keep this on, working on what we call the acetoacetate ester synthesis, very much like malonic ester. It's very, very much the same thing. And we're going to introduce two new reactions, Michael and Robinson. So up until now, too, each class we're telling you usually these patterns of other reactions. Yes, they have names associated with them, but the main thing as we work through these is look at what's common, right? All of these are reactions where we're taking enolates and we're adding to different electrophiles. The two things that have changed so far is enolates initially were the aldehyde ketone one. Now we've done a permutation, enolates from esters. Okay, electrophiles, aldehydes and ketones. Now it's esters as the electrophile. When we go up to these other ones, Michael additions, we're going to actually start targeting what we call alpha-beta unsaturated systems. But first, the acetoacetate synthesis, these are very much the same thing as the malonic ester. The only difference is you're starting with a molecule. Remember, malonic ester had two esters on both sides. These molecules have an ester on one side and just a simple ketone on the other. But functionally, we do the same thing. This is our way of, number one, I'm acidifying the protons in between, so it allows me to target. That is where I'm going to make my enolate. Number two, it contains a hydrolyzable group over here. I can hydrolyze this piece off to turn that into a carboxylic acid in between. And then that third step, heat and acid, that allows me to remove that carbonyl I've circled, the pink carbonyl or carboxylic acid can be removed as CO2. So what we're doing is that same synthesis where the target part of the molecule, this carbon fragment right here, is being retained. We're decorating it with alkylations, something type of an electrophilic species, and then we're removing the activating fragment, that ester part, through this kind of final step. But again, same idea as the malonic ester, only difference is over here we have a ketone. So let's work out this as a synthesis. Let's say we started off with this kind of acetoacetate type molecule. We're trying to build the molecule in the product. Now, this is one of those cases where what we've done is since we've done this alkylation, we've built up the molecule, and we've removed that CO2, your product is missing a chunk of your starting material that can make it a little bit difficult to recognize. So we start off with the pieces we know. Remember, if I am going to be doing, nice thing about this is that fragment there is the donor part of this molecule. I'm using this to target those middle two protons as the center I'm going to be decorating, which means I'm going to say that center right there is my nucleophilic carbon. That's the piece I'm building up. It's going to be attached to this carbonyl. So that fragment I'm going to decorate right there, where that center, that dot, is my nucleophilic carbon. So that's the first part. Is when you're doing this mapping over, the ketone fragment is the piece that's being retained. Find that ketone fragment in your product. So that's those three carbons right there. The rest of it, that's the piece that's being removed after our final synthesis. That means now we have two different bonds I need to make. It's this one right here and that one right there, which means this whole part here, I'm going to decorate this out. That carbon and these pieces, that is an electrophilic fragment we have to add. That's one electrophile we're going to bring to the party. And then over here, this carbon, this piece over here, that is a second electrophile I'm going to bring in. It's going to happen in 2 different steps. Remember, nice thing about these acetoacetate molecules, the malonic acid one, usually we're starting off where if in the middle, those 2 alpha protons in between, we have 2 protons, which means I can do 2 sequential deprotonations, and I can decorate it 1 at a time. So now I know I have to build up this fragment. I've got that kind of green electrophilic fragment and the blue electrophilic fragment. What I'm going to do is step 1, what should I do? Give me a reagent. If I'm making an enolate, what's a good reagent to apply here? Sodium ethoxide. Again, simple base, and because this is an ethyl, an OET fragment, that's kind of going to match your alkyl fragment as well. Again, not as critical as kind of the other ones where we're doing standard Claisen synthesis. That fragment of the molecule will be removed, so it's not quite like the end of the world if you happen to choose a different base, but generally good practice is whatever this fragment you're eventually going to lose is on that ester, you're reflecting it as your basic component too. So sodium ethoxide is going to give me my enolate. Next, I'm going to bring an electrophile to the party. I have 2 different ones to choose from. What do I have to do? There's the blue piece and the green piece. That's what you build in the end. Both of those are going to come from something simple like an alkyl halide. Anybody have a preference? Green or blue first? What are you feeling? It's Friday. Green, all right. It doesn't matter. There might be certain cases where if you imagine this, like let's think strategy for a second. We're doing our first addition, right? If my first addition here, this is the most nucleophilic the fragment's ever going to be because there's not a lot of other stuff on there right now. In certain cases, you might say, I will do the easiest step first because maybe adding that bulk, whatever, that green stuff, might make it harder to do that addition later. Basically, if you have a bulky electrophile, maybe do that one first because your second step is going to have to be harder anyway. Maybe a smaller one is better for that step. Methylation last or something like that. But it really doesn't matter. So we're going to do the green one. If I'm going to do the green one, I need those carbons. That carbon represents this dot I've seen over here. What's the other piece that's missing? It's going to be this isopropyl something, but I need a what? A halide. What do you want? Bromine, sure. Just don't do fluorine. So we're going to bring those 2 fragments together. That's our alkylation. Bloop. Wait. Bloop and bloop. No, not reversible. And that gets us back after this reaction, after workup, we will have our first installation. We got that piece added to it. Okay, we still have a proton left, which means I can take it through a second cycle. I'm going to deprotonate it again, and might as well use the same base. That's going to get me back my enolate. Looks a little different now. Because we have our alkyl fragment attached to it. Still nucleophilic. Now, the major difference between these 2 enolates, remember, this one is really only has 1 carbon fragment and a hydrogen. So it's more nucleophilic. We can add more things to this. That's where you could add alkylation or potentially another carbonyl compound. Once we're up here, this enolate is more crowded. The only move that these kind of dicarbon substituted enolates can be used for is alkylation. So what we're about to do here, totally in scope. Cannot use it for an aldol. Cannot use it for other sort of pi additions and stuff too. So we're going to bring in another fragment. It's going to be these 3 carbons and again, bromide or iodide. It's just a linear sort of 3-carbon fragment is all we need. Bringing that together, down, and our SN2 gets us our final compound after we've taken it through, right? Wrong. Don't jump so fast. That addition only takes you, we've completed all of our alkylations. We've got our 3-carbon piece. We've got our 2-carbon piece. I'll draw it down here. We still have to deal with the fact that our activating group is still in place. It's time to get rid of that ester. We need to clip it off because the center carbon is now this tetra-substituted center, and we want to reduce it down, or not reduce it, but we want to strip off the rest of this component. Yep. Say that again? Good question. If it could, honestly. The way you would have to control that is back to the same reasons that we saw before. If you're generating an enolate like this is something where you'd have to either add them at the same time, potentially, where you're generating the enolate in the presence of the halide, or keep the temperature appropriate. You're right, this could undergo like a self-Claisen type condensation, and usually that would be controlled by either concentration or how much bases you're adding to the system. Time is probably your friend here. So you can generate it in this space where we're making this component, and then the second is the addition of that enolate. Also possible, right? You could imagine doing this where sodium methoxide is being added to a system where that alkyl halide is already present. So as the enolate is formed, it's being grabbed by the alkyl halide. Yep. Sorry, say that again? Exactly, yeah. This is all something where what you're doing is you're balancing all the different rates. You're right. Sodium ethoxide could still act as a nucleophile, right? There's still a possibility of that. Since this is a process where you're going through and you're trying to do this where how much you add is basically going to help to dictate it. Sodium ethoxide will add, but generally that will be slower compared to the enolate addition that you're doing in this case. So, last step here to cut all this part back down. You're going to do this with usually acidic conditions, H3O plus in water, and heat. That'll carry out our saponification. It opens up our carboxylic acid. Once the carboxylic acid is opened, it'll undergo the decarboxylation using that pericyclic 6-member transition state to extrude CO2. So, I want you to continue this part out. This is something I want you to do as a next one. Similar kind of a starting material. Difference around here is your product is undergone a similar kind of transformation, but we've done one more thing. If you notice here, we've done another transformation at this functional group here, which is the next step after. What I've been showing you up until now is these sequential alkylations to build up these structures. But as we get more complex and you bring in other functional group transformations from the other parts of the class, it gets a little bit more complex to identify those. This is where potentially working backwards from something like this can be really helpful. So, next reaction is what we call conjugate additions, Michael additions, or additions to alpha-beta unsaturated carbonyls. So, if you remember this, we introduced these compounds to you guys. This is where we have our aldehyde or our carbonyl, and at this position here, we have a group which is in conjugation in resonance with that carbonyl. We usually call these 1,4, or we usually call these alpha-beta unsaturated because of these two groups in these type of positions. Remember, they're the products of our aldol reactions. This is our condensation product that we get with the addition of an aldehyde with another aldehyde plus the extrusion of CO2. If you look at a molecule like this, where is it electrophilic? So we've got a delta plus here, delta minus over there. Where else? Now we've got this double bond in presence there. Where else do you have an electrophilic site? Where's that? Yeah, like remember, if you draw out the resonance patterns across this one, this is in resonance in this way, right? The double bond can slide over and then punch up to kind of partially drawn towards the electrophilic nature, the electron withdrawing component up over here, which means this center over here is also electrophilic, right? This is an extended carbocation. Remember protonating these ones when we did those things about like deuterium exchange? Having that double bond acts as a transmitter of these kind of other characteristics. So you have this two different electrophilic sites. The parent one right here at that nature of the carbonyl, but we also have this more extended one at the end of the double bonding system, which means these are just electrophiles. And more importantly, they are still pi electrophiles, just like a carbonyl. These are carbonyls one longer equivalent than the ones we've done before. So why this becomes sort of an exact match to the aldol type reactions, remember aldol is an enolate attacks another carbonyl. Enolate attacks an aldehyde. Enolate attacks a ketone. Having this double bond attached to it means this becomes the target of our electrophilic addition. What we're doing is we're adding to this center now, which gives us a slightly different attack pattern. So these alpha-beta unsaturated carbonyls have two different kind of species, or you look at them as two potential different ways. Very similar to what we talked about with things like the HWE and the Wittig reaction. If you have really, really reactive nucleophiles, things of like Grignard reagents, those will typically go after the end of the molecule. Now, in a case of an aldehyde, aldehydes are always going to be really, really electrophilic. What we call the 1-2 addition, and that numbering scheme is talking about 1, 2, the two atoms across this point. So adding directly to the carbonyl is usually something that we see with what we call hard nucleophiles, Grignard reagents. That's just because they're irreversibly being added to a very high energy anionic species. So things like Wittig reactions and stuff would typically add directly to the carbonyl. If you have less basic systems, things where they're slightly more stabilized nucleophiles, these undergo what we call 1,4 addition, which are at this center over here. And again, that's 1, 2, 3, 4. We're talking about the atom chain that's involved in this addition pattern. So these are things like enolates, enamines, these kind of soft nucleophiles, the ones we've been talking about in this last chapter, will typically add to the 4 position, which means they're a little bit more distal away. This is a thermodynamic kind of an addition where you end up with a more stabilized product. And again, that's just because what you end up in the end is you preserve your carbonyl and you're just adding to this distal site over here. So it gives us a couple different patterns. Now that we've got these enolates, and we've been using enolates directly adding to an aldehyde, enolate adding to things like esters, this is just your next permutation of what your electrophile is going to be. So with that component, usually what you're going to get is enolates, and particularly doubly stabilized enolates, the ones we've seen from malonic ester synthesis, Canova-Nagel type additions. Those are typically the ones that you're going to use in this sort of reaction pattern. Those are the most common sort of ones that have this very strong 1,4 type addition pattern. So these are the ones we use to build up these fragments. And they're very useful because we can build some very complicated structures pretty quickly. So the general name that we give this, conjugate addition, is just nucleophilic addition in a 1,4 kind of pattern. That's generally the overall reaction that we talk about. That's the attack pattern. What we call Michael addition is just an enolate adding to a alpha-beta unsaturated system in specifically a 1,4 pattern. So that's our 1, 2, 3, 4, where we're adding that center is the electrophilic acceptor. And as we say here, and as I was mentioning before, the nucleophile we're using in this case, we're using a simple base, and we're using these doubly stabilized compounds, something where we've got alpha protons and then two stabilizing groups like we saw with the Canova-Nagel reaction or something like the malonic ester synthesis. So the bond we're forming in this end is this new bond right here between that nucleophilic center and the electrophilic center. We're effectively adding across this double bond. We end up with a carbon-carbon. More importantly, there's no more pi bond, no carbon-carbon pi bond anymore either. This has been replaced. That means that you've got an addition of a proton at that center as well. And we'll show you how that part gets in. So effectively, think of it just like hydrobromination. You have a double bond. You're adding a nucleophile and a proton across that double bond. That's what we're doing over here. We're just using a carbon anion adding to the 4 position and the interior position. Alpha to the other carbonyl is getting a proton in the end as well. Yep. Oh, if you hit this hard enough with a base, yeah, you could deprotonate out over there as well. Yes, that's called an extended enolate in that point, but we're not doing that. No, again, how we would control it, but really good question. In a case like this, how we generally control it, and that's why we use conditions like this. I'm pairing the system up where my 2 pink protons I have here are so much more acidic that they become my obligate nucleophile. You're right, if I took something like the alpha-beta unsaturated system you see over there, the ones in green, if I had another center and if it happened to be basic enough, I could potentially make that enolate. But what we're doing in these cases, and this is why we use these doubly stabilized systems, we're making sure that the nucleophile is only the one between those two other carbonyls. We're trying to steep it away because the pKa of that other deprotonation would be far higher. So yeah, these are your common nucleophiles you're going to use. And again, you've seen them before from what we call the Canova-Nagel reaction. You see that up at the top, those are like our malonic ester synthesis or the acetyl-acetate synthesis. Every one of these common Michael donors, or the Michael nucleophiles, they're stabilized between two different carbonyls, like our standard component. This is our malonic ester kind of system. Anything where we swap out the group instead of just a ketone or an aldehyde to an ester, that's also possible. Remember, swapping out the ester oxidation state to something like a nitrile, those are also equivalent. We get this resonance stabilization. The only other one that you see sometimes are these nitro components. So we have a nitro ketone component, where in between we still have that center. All of these, what's common is you've got this kind of double carbonyl or some form where an anion that's generated in between can be resonance stabilized to both groups, either side of it. So two adjacent groups are stabilizing out. Very much similar to what you see with things like HWE, right? The negative charge in between these two is being stabilized between both. The only reason, like an HWE reagent, this guy here, these guys do not show up on this term because these guys, that phosphorus that you have on that other group, that becomes a leaving group, which is specifically used for olefination. So what we're doing is the same conceptual part that we did before. Don't use the phosphorus, because what that will do is it opens up this pathway to do an oxygen extrusion reaction. Remember, this is our reagents that we would have for our normal HWE. So we stick exclusively to these other carbon nucleophiles in order to get our Michael addition components. Yeah? This one? It can actually. So usually that's why these pairings, once you've got that center, it's the oxygen both sides, right, are nucleophilic. The charge is going to be at those centers. Typically, those kinds of things, if you wanted to hit the oxygen, you'd have to use an electrophile like usually, it typically ends up being things like methylations and stuff like that. Since we're using these as nucleophiles into pi systems, that pairing means that you're never adding via the oxygen, you're only adding via carbon-carbon bond. But so yeah, decorating those other sites usually means a different nucleophile would be necessary. Or excuse me, a different electrophile would be necessary.
Why do we need double stabilization of the nucleophile?
It comes back to partly this. If we're doing this addition, and again, when we start to put all these pieces together, there's a number of different permutations that are possible. We're trying to say that if I could add to two different centers, here or here, this is kind of like back to what we talked about with HWE, right? So what I'm saying is, if I have a nucleophile which is doubly stabilized, it's not an unstable component, which means it could add, eliminate, add, eliminate. It allows me to access the thermodynamic product from these additions, right? Just like HWE, where sure, you can attack, but if you have to pass through a relatively unstable intermediate, it could still back off again, reform the anion, and still come back together. It gives us our selectivity because what we have here is these molecules have a bunch of different electrophilic centers, and we're trying exclusively to say, I only want that addition to happen. It gives us back control. So this is thermodynamic control is what we're trying to build in. So our acceptors that we do here, if you look through these are all alpha, beta, and saturated systems where you have a pi bond that you're adding to with some other acceptor in. So these guys, this is your aldehyde, your ketone, the ester, those are the more canonical ones. The amides, these things here, interesting fact, these kinds of molecules are actually the core thing that we use right now for a whole new cancer therapy that's been sort of invented over the last couple of years. These are what are called covalent inhibitors. Molecules like this, where that nitrogen might be attached to a peptide, it allows you to put this little warhead, this little alpha, beta, and saturated system, this part hung over a larger peptide, and it basically acts as like a mousetrap. You can actually put this on a small molecule, and what it will do is dock according to what the small molecule function is on a surface of some type of a peptide or something else that's involved in a cancer therapy. And what happens is that molecule, that cancer cell, will see a molecule like this and go, well, there's that electrophilic center there. Maybe I'll just kind of get close. Ha-ha, gotcha. So what you're doing is you're using a molecule like this as both the bait and trap. And putting the two pieces together means you can kill selectively cancer therapy by having something like this that's a very dangerous warhead molecule, but will only ever localize wherever that sort of functional group over there is. It's a whole series of what are called degraders and other sort of chemistry that's been very interesting the last couple of years. These are a little bit different. These are still nucleophilic addition to that center. This is the electrophilic center we're dealing with in that case. But remember, we can swap out that higher oxidation state. Instead of an ester, nitrile is equivalent. It still has that pi bonding system adjacent to it. These are our vinyl nitro systems, ridiculously powerful 1,4 addition components. And again, very good because they really only attack at that carbon center, not on the nitrogen. So, but the pattern you're seeing here that is across the generic part is that still that you've got these two different components. A nucleophile that is this doubly stabilized species. It's got two different protons in between that we're going to deprotonate, and then we're stabilized by two different resonance structures on both sides. The electrophile is this alpha beta unsaturated system where we've got some type of a carbonyl at the position over here where we're trying to target this kind of 1,4 addition pattern. The product we make in the end are these more extended structures. You're building up a lot of carbon skeleton very quickly by doing this. We're fusing together both this structure over here in our nucleophilic fragment and then the electrophilic fragment making up the bottom part across there where the red bond is our new part. And again, thing else to look at this as well, the addition we had where the double bond used to be was right here. That means that there's also a proton being added to that center which used to be alpha to that alpha beta unsaturated system as well. We'll show you how that part goes through because it's coming through what is like basically another enolate addition. So the overall mechanism, it opens very much the same we've seen before. We take our base. The base is going to form our enolate. So just like malonic ester synthesis, the canovinagle, the aldol, all of them are opening with this same addition. Now that we've got this fragment, we're going to bring in our alpha beta unsaturated system. This is our pi bond. And again, you can decorate it generally broader from this as well. Now that we've got our nucleophilic fragment, what we're doing is we're bringing in that addition. Now, instead of the addition to the carbonyl, we're going to attack the 4 position, and then it's a sequence moving that bond across that entire sequence. Now remember, this is not just a normal pi bond. The pi bond here, because it's in resonance, it's polarized. Having that carbonyl associated next to it means that we've got this electrophilic site and that distal position, which pulling electron density over, so it allows us to add to it, and it slides the bonding over. So what we end up after that addition is our nucleophilic fragment regenerates our carbonyls. We have the new bond we just generated, still a proton left over here. And this center here, the end is this center here. All we've done so far is we've slid over the double bond and we've regenerated. If you watch the pattern right here, that negative charge, pulling this charge over here and up onto that oxygen, what we just did there is we made an enolate. We've parked it up onto that center. So this is very similar to addition to a carbonyl, right? We add to a carbonyl, we're parking negative charge up onto that oxygen to make this alkoxide. So what we're doing is we're adding through here, we create this enolate-like structure, and now, remember, the properties of an enolate, if I'm this enolate, that center right here, this is nucleophilic again. The enolate that it generated can be protonated now. So this is how we get that second proton added to the system. After I've done this addition, remember the other part of this reaction here is I've made one equivalent of water. I've temporarily transferred my proton over to my base. Because my carbon, the first enolate I make adds to this 1,4 addition, what I've now made is an intermediate enolate. That intermediate enolate wants to collapse. We want to bring down that negative charge, right? If this was something like an acid addition to the Claisen reaction, we would normally be kicking out a group or something else. But to reform that pi bond, bringing down this oxygen, means that double bond can act as a base and pick off a proton. So it becomes this kind of, what you're doing is this very extended sloshing of electrons. The enolate from your starting material is adding in this 1,4 addition. It punches over to make an enolate intermediate. That enolate intermediate then can pick up a proton to protonate to give us back our product. So just dialing out where everybody ends up going. You have your new bond. This will now be a carbonyl again. And we've added a proton to that center over here. So what used to be this carbon-carbon pi bond across here, one end of it, the nucleophile is ending up on the furthest position, the 4 position of that double bond. This center here, that's the kind of the nucleophilic part of that alkene, is picking up a proton. So it's a proton-carbon addition across that bond. So that's the overall sort of sequence into it. Nucleophile, you generate your base, or with your base you generate your nucleophile. Once you have your nucleophile, you're doing a 1,4 addition to give you your new carbon-carbon bond. That generates this intermediate enolate. That intermediate enolate then picks up a proton at the end. Yes?
That enolate you make, that's nucleophilic. Is it possible for that to add into another equivalent of the alpha beta unsaturated?
Not usually there. Again, nice thing about this one is it's usually very, very short-lived, so usually protonation is good. You're usually running under conditions where, remember, what you've done in terms of relative stability, we started with a way, way easier to form enolate, so it's relatively acidic starting material. You've made a much less stable enolate as a product, right? What we've done is we've made this enolate that is now going to have a much higher pKa because it's usually this is not doubly stabilized anymore. So protonation is favorable, at least as you have an environment there. Now, right, if you had a high enough concentration where you could generate this, that might be a case, but usually keep the concentration low enough. If you only make a little bit of this intermediate present and it's in an environment where there's lots of protons around, protonation will always be faster. But I'll show you in a second one of the other things we can do. There are intermolecular reactions you could potentially do where you could capture it in some other way. But finding another equivalent, like a second molecule, is a little bit harder. So the protonation is usually favored because, again, it's under conditions where we've got a protic solvent or something else to help to quench it. Yes? Yeah, you can. Like not multiple alkenes, but usually an addition like this, what you formed here, I've made a product where that product still has a proton, right? Like you could look at this and say, now that I've done this addition, I might go back, treat this with base, and then do something else with this one, right? I could potentially regenerate the enolate up at this top space here in order to do another alkylation. The downside with that is that enolate that we would generate, so let me draw that out. Let's say, hypothetically, if I treat this with base and I make this, so look at the substitution pattern of this center. Yes, you could generate this enolate. That enolate has 1, 2 carbons attaching to it. I can alkylate this. I could use something like a methyl iodide or something else. But I can't add another equivalent of a pi system. It will never add another alpha beta unsaturated system easily. This is really, you're trapped in. So that last move usually has to be just simple alkylation. So let's take it through here. You've got an alpha beta unsaturated system. You've got this malonic ester. We're going to take it through this addition to draw out the product. So this is going to be our donor. We have our protons. This is going to be the acceptor. We're doing it under conditions of we've got ethanol and we've got sodium ethoxide. So we put this all together. That'll let us make, in the reaction mixture, our enolate, and that will add in a 1,4 fashion over here. So if we're trying to target out which centers end up where, that's my nucleophilic carbon. This is my electrophilic carbon. I redraw out the nucleophilic fragment. That's my electrophilic center that I've added to. This is the nucleophilic center. And when we add, like we say, we call this a 1, 2, well, it actually counts back from the carbonyl, 1, 2, 3, and 4. That's what we call our 1,4 addition. So 1, 2, 3, carbon number 4 is this one over here. So it puts the carbonyl down in that position 4 atoms away from where it adds into it. So this would be the addition position we would get into. Now, in a molecule like this, under these conditions, this is just the addition fragment. If we wanted to, we could carry out that second closing like we've done before, treating this with acid, removing those esters, and then decarboxylating would allow us to sort of trim down that fragment as well. So we'll carry this through in the next one. So now, this opens up what we mentioned before. If I've done these additions, the molecules I'm now making by this conjugate addition, they're valuable because what we can do is I can add this fragment, I've installed another carbonyl, and now I can bring in any of the other permutations we've done with other carbonyl chemistry. The most common one we have, again, is around ring formation. That's what this was named as what's called the Robinson annulation. The word annulation we're saying there is this formation of a ring. What we're doing here is actually a Michael addition like we've seen before. The Michael addition is between our doubly stabilized nucleophile and the conjugate addition. Once we've made that product, though, your product has a whole variety of carbonyls. Yes, we have a bunch of other centers, but more importantly, there are still alpha protons in a couple different places on this molecule. So just like we talked about before with intramolecular aldol reactions, if I have a molecule that's sitting around like this, treating with base will allow me to potentially deprotonate any of those alpha centers. I can regenerate an enolate. If the right enolate is generated with either the geometry or reactivity to what some other part of the molecule, you can get a ring formation to happen. And like before, 5- and 6-membered rings are generally ones that you're targeting. Usually with Robinson annulations, you're always making these very constructed 6-membered rings. Overall, the first Michael addition installs that bond. That's what extends this other fragment. If you continue to react, or with more base, yes, there are 3 different alpha centers, but the one that's unique about this alpha center here, the position of it, if I deprotonated there, is exactly 6 carbons away in order to make that bond down here. I can do this intramolecular aldol reaction with this other fragment. When that comes in, that's the aldol reaction. Aldol condensation allows it to collapse to a double bond. So we're now bringing together 3 different reactions from this sequence. First of all, the Michael addition to give us this longer fragment. Then we're doing an aldol addition, intramolecular aldol addition to make a 6-membered ring, and then an aldol condensation to give us a double bond. This is all under thermodynamic control up until the dehydration. Yeah?
So for that, like in the top row, the initial Michael product, is there anything that you can do with the other 2 alpha centers, like on the other sides of those carbonyls in the ring? Is there anything you can do with those?
This one here would be easy to do alkylation. That's possible. You could do chemistry here as well, but the nice thing about a molecule like this, if I can make an enolate here, I can also make the enolate there. It's very difficult to select left or right. So why I'm getting reaction here and not there is because of the ring geometry. If I have this molecule, both the donor and acceptor are in the same molecule, that ring closure gives me a reaction between the two. If I'm trying to get something between an intermolecular reaction, it's a little harder to select for.
I was also just wondering, like, these 2, like, do you use
as alpha
centers?
They can, yes, but again, I'm in that sort of case too. Then this is just like we talked before. Sorry, let me go back. Good call. What you're mentioning is this guy down here, for example. Well, let's say we did that one here. Let's say this one attacked that center, right? The downs, because in the end, it's possible to do any intramolecular aldol. Remember, 5 versus 6 is the thing that you're targeting. A guy like that, the 2 red centers I've just highlighted there, that forms a bridging between different points. You have to reach across the ring, so it's disfavored. It ends up with these planar structures that sort of comes out in the end. Yeah?
What are
Why don't we form the tetrasubstituted, which?
The tetrasubstitute.
Which one, sorry?
In the final step in the dehydration, why didn't you form the dicep product and eliminate the tetrasubstitute?
Oh, okay, so you're saying, wait a minute. No, instead of this one?
Yeah.
It could easily migrate after, right? But what we're showing for the, like, in the end, the elimination we're showing here, this exocyclic one will generally be favored instead of putting the double bond inside the ring. The tetrasubstitute one across the bridge is going to have a lot more ring strain associated with it, right? Because that's a 6-membered ring in the middle. If I tried to bridge it across here, you're really compressing those 2 rings together, right? You're going to take all those and have to make them planar, and they're tied together around the outside. So generally, exocyclic is that's going to be used. So let me walk you through this one. Step 1. We're going to do our enolate generation. Step 2. We have our electrophile. So my nucleophilic center here is going to grab electrophilic center over here. I make a new bond between the two, and I end up, after the enolate generation of the components, with this guy. So that's what I've done there, is I've added that 4-carbon fragment across here. That is my electrophilic center, my nucleophilic center. The green designates the new bond. And I've completed the enolate protonation. So that's following the Michael addition mechanism. Then we come back with more base and generally higher temperature. The 2 reasons we're doing this is we want to make sure that we're forcing the enolate generation to something like the aldol. The heat is there because we're trying to promote, eventually, aldol condensation. So this is back to the, we're not trying to select for just the aldol reaction, but the aldol condensation as well. In this case, generally, that distal center over there ends up being 1, 2, 3, 4, 5, 6, which means we're adding back to that center over here. That gets us a 6-membered ring. So just after that aldol addition, I'm going to redraw that part first. Green here. This is our carbonyl. Got these parts. That center's here, blue center here, pink center there, red center there, with our new bond between those 2 centers. After this one, now we're going to do an elimination. So by heating this, high temperature, under basic conditions, we're going to get our final compound. Green there, light green over here. Bonds there. This is our electrophilic center, nucleophilic center, second electrophilic center, second nucleophilic center. Where this either here, or in this case, you could have either the 2. The elimination from that red carbon could give you 1 of 2 possible isomers, but we end up with a double bond in the end that locks in this cycle. That's your final component. Now, why that is super cool is because that is your cutoff for midterm 2. So, again, we'll practice this point, and I'll show you a couple other ones online. Have a good weekend, guys. Okay, so for these questions, we're going to do a synthesis using the acetoacetate route. That's this molecule you see here. And we're asked to synthesize the following compound. Now, when you're doing these synthesis ones, an important first step is to basically locate which atoms from the starting material you've been given are showing up in your product. And you can see the cyclohexane ring is probably new. It's not represented in our starting material.
And if you remember the acetoacetate synthesis, what we're doing is we're using this double carbonyl pattern to acidify these protons. And the goal of that is to make this center in between our nucleophile. That's where we're going to be coupling other things onto it. And remember, after the reaction is done, a chunk of it is going to be removed through the saponification and decarboxylation part. So these 3 carbons are probably the part that's going to be actually transferred. And then just to denote their role, this would be our nucleophilic carbon. It's the one in between the two. The carbonyl is a key one to look for. And then there's going to be a methyl group attaching over. And looking at the product, this would be our nucleophilic carbon, the thing that now has other things attaching to it. Carbonyl carbon, this one, now granted it's not a carbonyl anymore, but we're going to modify the oxidation state, and that's this methyl here. So that's probably those 3 carbons, which makes this bond, the new bond I'm going to be forming, right? So I'm going to be making this bond here, and that makes this center some electrophile that I've added onto it. It means I can bring this whole piece in as my electrophile to make this carbon-carbon bond in between. So the route I'm going to use is going to be something like sodium ethoxide. That's going to make my enolate. Then I'm going to bring in the electrophilic portion. So that's going to be my cyclohexane ring plus 1 carbon. That center there is the one I'm actually attaching to, and let's make it as, let's say, the bromide. Could be the bromide, could be the iodide. Either is possible. The addition I'm making there is going to give me this product after that step. So we would have back our 2 carbonyls, the O-ethyl ester. The new bond between these 2 centers has now been formed, and we've got the attachment of this electrophilic fragment. So that green center there is the one we've been tracking through. The nucleophilic center, this one here, and that maps out back to our starting material and towards our product. And again, just finishing it off, that's my carbonyl and my methyl group, just to kind of align you with where we're trying to go over here. Okay, so now we have to take care of this chunk, and that's our workup step, or our sort of protection step. So that's going to be under acidic conditions with water and heat. That's the 2 things we're doing is, first of all, converting this to a carboxylic acid. That's really the function of this acid and water. The heat over time is the decarboxylation. So remember, there's 2 steps embedded in this overall process. The outcome after those 2 will be simply this. So to map it out, that's still my carbonyl. This is still my nucleophilic carbon. That's still the electrophilic carbon, and this methyl group. Everything else has been lost in that step, so we're making CO2 and ethanol as we do that. Now to get to our final component there, we just have to reduce the center, so this would be something like sodium borohydride, which will get us down to our alcohol. Okay, now we're going to do this addition here. You can see we have our nucleophile. This is going to be the molecule with our 2 protons in between. This is our stabilized enolate that we're going to be forming. And the electrophile, this is our Michael acceptor. It has that alpha beta unsaturated point. Now this is symmetric, so you can sort of think of it as that's my alpha beta unsaturated piece, or this is the alpha beta unsaturated piece. Both of them are identical. You'll get the same product in either case. So under basic conditions, we're going to make our electrophilic molecule. We're going to do an addition to this center. So that's my nucleophile. Pink center is my electrophile. That's going to be adding to here. So the new bond is the one we formed in between, and the conjugate addition will give me the rest of this fragment. So the rest of the molecule will look like O-ethyl, and then here O-ethyl. Okay, for this one we are doing a Robinson annulation. What that means is we're going to be doing a conjugate addition reaction that requires us to have alpha protons to make an enolate, and we have one that's there and there. and we're going to do a nucleophilic addition to the acceptor. This is usually, the first addition is going to be to a alpha beta unsaturated system. Remember, Robinson annulation is actually both a Michael addition or conjugate addition and then an aldol condensation. So nucleophile, the donor, is going to be one of either this step or this step. However, since we have only one alpha beta unsaturated system, this is likely our acceptor, and that makes this the donor. There's one more good reason why these two protons here in blue are going to be favored relative to, let's say, these protons in red. Remember, the pKa here will be much higher because these blue ones are doubly stabilized both by the carbonyl and the aromatic ring. So these blue ones should be more acidic. So we're going to do our base deprotonation. We'll make the enolate at that center, and we will do a Michael addition first. So I'm just going to draw the product of that Michael addition using the donor center I've designated over there first. So let's draw this out. This is our donor molecule. That's our nucleophilic center. And that makes this our electrophilic center. We're going to make a new bond here between those two fragments. Then we have our acceptor like this. So that's the first step. That's the conjugate addition for the Robinson annulation. The now second step of the Robinson annulation is an aldol condensation. So once again, we need to look at where we have alpha protons, and now in fact we have three we could consider. So this light green, we have dark green over here, and then let's say pink center over here. All three are possible. Now, first thing we want to do is eliminate centers that potentially the ring would not be allowed. So for example, if I were to deprotonate at this center here, that would make the green center from here my donor and the carbon over here my acceptor. But if you notice, that's only 1, 2, 3, 4 carbons. That is unlikely. A 4-membered ring from there is not going to be favored, so I'm going to eliminate this one as a possibility. That's not going to be considered any further. So now we only have our dark green and our pink center. Starting from the pink center, if this was my donor, the carbonyl over here would be my acceptor. That is 1, 2, 3, 4, 5, and 6. Okay, that's possible. So that's at least allowed right now. And notice in both cases we have ketones in both places, so the two possible acceptors are identical as well. So this one is a maybe, because we get a 6-membered ring. If we go from the other side, so from here is my donor, that makes this the acceptor. That is 1, 2, 3, 4, 5, and 6. Okay, so from both of those two centers, from either the pink protons or the green protons deprotonating at either of those centers, gives me a possible 6-membered ring as well. So in both cases, we have a 6-membered ring that I could generate from either of those two additions. So now we have to discriminate by something else. One of them is going to be preferred over the other, and that's where you could look back to the pKa's. Here, if I make the enolate at that center, so the corresponding enolate I would generate would look like this. It is only stabilized by this one carbonyl. However, the enolate over here, if I were to generate that one, is now doubly stabilized. We have the aromatic group as well as the carbonyl. So this is a more acidic center. So I'm going to favor the addition from this green center, which makes the other carbonyl, the pink one, is no longer in scope. It's going to stay that carbonyl, which makes the role of the two. The green one will be my nucleophile. This pink center here is my electrophile, or in other words, donor and acceptor between those two. All right, so now if we're going to do this, actually just to change the color so I can designate everybody cleanly, I am going to use a different color so you can track each of the other carbons. Actually here, let me redraw this real quick. So I'm going to use, because I used blue and green over here, I'm going to use red to designate that nucleophilic center, and I'm going to use pink to designate that electrophilic center. So that way we've identified a couple key carbons in this addition. So we're making a six-membered ring. The six-membered ring is going to be made up of these atoms through here. So I'm going to bring the center over closer to that side to give us a just visibility to the new six-membered ring we're forming. So we have this carbonyl. We have the original bond we formed from our Michael addition. We have the 3 carbons over here to our electrophilic center. 4th carbon is our methyl. This is our new electrophilic center. This was the first electrophilic center. Here's our first nucleophilic center, again with our aromatic ring, just completing it out over here, and second benzene over here, where the nucleophile is that center over here. And now that we've done this addition, we will have a new double bond connecting those 2 centers in between. That is because we did an aldol condensation at that center between the red and pink center. Our donor acceptor is both the aldol addition and then condensation reaction, which gives this as our final product we're generating in this case. Remember, we're basically making not only the ring size, but we're also making 2 new bonds as we go through this. We're making the first one from the conjugate addition, the second from the aldol condensation. Now for this one, we're asked to sort of walk backwards. Now remember, we're still doing a Robinson annulation, and we need to reverse it working backwards. So if you remember the Robinson annulation, the final step is an aldol condensation, which gives us an alpha beta unsaturated system. So this is probably the functional group we're going to form from that center. So to kind of reverse it, first thing we're going to do is reverse the aldol condensation and go back to just the aldol addition. So what that would give me, if I just redraw, same molecule, phenyl group over here, methyl over there, carbonyl, carbonyl, and O-ethyl. Adding back water would give me OH and H. That's the aldol addition product, where again condensation across here reforms those 2. Okay, so that's the first point, which means the next thing I'm going to do is fragment that bond. That's the aldol addition reaction I'm now reversing. So that would get me back to just ketone over here, O-ethyl ester, and we've got carbonyl and phenyl. Now, just being more specific, that what we're doing here is this would be my donor, and this is my acceptor, which gives me my aldol addition reaction between those 2 centers here, and that maps back to the original product in that sort of way here. So that's the sort of the pieces we've broken through. Now we're ready to break into the conjugate addition. Now in the conjugate addition, we are looking for what used to be the alpha beta unsaturated system and another donor. Now notice that we've got this kind of double stabilized nucleophile looking thing. If we had this as my nucleophilic center, that would make my stabilized enolate for my ethyl acetoacetate type fragment, and then that makes my my acceptor, this carbon right here. So if I was to fragment that bond, we go back to our 2 pieces like this, O-ethyl, and then this part would just become the alpha beta unsaturated system like this. And that means green center here, pink center here, nucleophile right there, and right there. So that brings those all pieces together. And mapping back to our starting material, again, that makes this was the nucleophile attaching to there, and then the second electrophilic center is here or here all the way through.